Hello, everyone. My name is Xufei Fang. I'm currently working as a group leader in the ceramics division headed by Professor Jürgen Röde at Technical University of Darmstadt in Germany. At the same time, I'm also affiliated to Karlsruhe Institute of Technology in Germany and Osaka University in Japan. Before I begin, I must regret to say I feel sorry not being able to attend this conference on site to have more in-person interactions with some of you. But I would really like to thank the organization team, especially Mr. Jonathan Foreman, for making this possible for me to present online. Today, I will be sharing with you the mechanical tailoring of dislocations in ceramics at room temperature. And I would also like to thank the editorial team of Journal of the American Ceramic Society for selecting me and this paper as the winner for the inaugural second century Trailblazers in JACerS. So my talk will be divided into 6 parts. And to begin with, I would like to briefly introduce to you what dislocations are. And for some of you, this might not be that straightforward. So dislocations are the main carriers of plastic deformation. And dislocations are also seen as line defects or one-dimensional defects in crystalline solids, for example, in metals and ceramics. And dislocations has been very well studied in metals. And in comparison to dislocations in metals, the dislocations in ceramics may carry charge at the dislocation core regions and surrounded by the space charge layer for the charge neutrality. And together, coupled with the high string field around the dislocations because the high lattice distortion, this actually brings us a new perspective of using dislocations, for example, to tune different type of physical properties, such as electrical connectivity, thermoelectric performance, ferroelectric properties, and even surface reactivity. So I will show you several examples later. And this brings us a new perspective of rethinking ceramics engineering for dislocation technology. For example, here I showcase the example of using single crystal barium titanite deformed at high temperature, where we can introduce dislocations. And this has helped to improve the large piezoelectric signal D33 star by almost 19 times. And this is mainly due to the dislocations we imprinted in the first place, that they started pinning the domain walls and helped to enhance the electrical mechanical properties. And due to the time issue, I will not go to the details, and I would like to recommend you to read this paper from our ceramics division. And another example is high temperature deformed titanium dioxide, where the dislocations are proven to be effective to enhance the electrical conductivities. So in order to achieve all this type of functional properties, the prerequisite is actually to successfully engineer dislocations into ceramics and without breaking them. So here I would like to give you a brief overview of the methods to introduce dislocations into ceramics, which can be mainly divided into 2 parts. The first would be processing and fabrication, and the second would be through mechanical deformation. For example, here, this is the example of a bicrystal alumina fabricated by thermal diffusion bonding. So simply put, you take 2 single crystals and bond them together with a specific tilted angle or twisted angle. You will be able to engineer the edge or screw type of dislocations at the grain boundary. By the way, this is the grain boundary, and the dislocations actually are threading into the paper or into the screen in the 3D dimension. And another example would be the so-called flash sintering technique. As you can see, the grain body here is subjected to the electric field and also electric current flow. And due to the highly non-equilibrium process, dislocations can be generated or maintained in the bulk. But the challenge of using this technique is, besides dislocation, we can also see a lot of other type of defects. For example, voids, pores, grain boundaries, and making the scenario rather complicated to solely study the dislocation-based mechanical and functional properties. So when we come to the mechanical deformation, it has been well known that in history, the high temperature deformation has been widely used to achieve plastic deformation of ceramic materials. being either single crystal or polycrystal samples. Here is one example showing the single crystal alumina deformed at 1400 degrees C. As you can see, we can actually even achieve roughly 10% plastic strain without breaking the samples. But the temperature is extremely high. And another way to engineer dislocations through the mechanical deformation would be rather through the so-called microscale or nanoscale deformation, which we can even achieve at room temperature, and will also be part of the focus in this talk today. As I mentioned, the key bottleneck to achieve the dislocation technology mentioned before is to have successfully dislocations engineered into ceramics, which are very often brittle, especially at room temperature. So currently, there seems to be a lack of efficient dislocation engineering approach. Even if it is the high temperature deformation, as we can see, sometimes it does not really guarantee a successful deformation of the single crystals. And the challenges for high temperature deformation is also evident. For example, the energy consumption and the time consumption, as well as even some discrete and limited plastic zone. And here is actually another example showing the so-called discrete and limited plastic zone within a large single crystal. But the plastic deformity region is actually very limited, making the rest of the crystals rather wasted, although this is actually achieved by room temperature deformation. So in our group, we have been trying to achieve the following objectives, rather to instead of doing high temperature deformation, we're thinking whether we can achieve even intermediate temperature or even room temperature deformation to accelerate this whole process. And also, compared to the discrete and rather limited plastic zone, can we also achieve large and continuous plastic zone for the easy handling of the samples? And it has also been shown in literature that the higher the dislocation density, actually the more beneficial for both the mechanical and functional properties. So in general, we would like to make the efforts also much more efficient and cost effective. So in the next couple of slides, I would like to show you the so-called overarching engineering principle for dislocation engineering at room temperature. And later I will focus on the dislocation, nucleation, multiplication, and motion, the three key factors I will focus on to explain by showing concrete examples. And in the end, I would also give you an overview of the toolbox we have developed in the last 4 years for engineering dislocations. So when we look at the mechanical deformation of ceramics, and in comparison to metals, we need to pay attention to, besides the possible plastic deformation, and in this specific case, also the crack formation, which are more prone to happen in ceramics because they are usually considered brittle. So that means we need to look at the competition between the plastic deformation and also crack formation. And in the specific case for the dislocation-based plasticity, so we would like to break it down to dislocation nucleation, multiplication, and motion. By nucleation, that means generating dislocations from 0 to 1. So from the original dislocation-free region to have dislocations to start with. And multiplication, of course, is, I call it from 1 to n. So from a couple of dislocations to many more dislocations. And of course, we need to make sure that the dislocations we generate are able to move. Otherwise, they will just become pinned and pile up, and that would actually eventually lead to the so-called dislocation-based crack initiation and further crack propagation, which we actually would need to try to suppress or avoid. And due to the time, I would actually focus mainly in this talk, the dislocation-based plasticity, and for the rest of the crack-related studies, I would refer you to this paper. Okay, so if we look at the three K factors, dislocation, nucleation, multiplication, and motion, our studies in the last years have shown that we need to avoid the so-called homogeneous dislocation nucleation, meaning that generating dislocations from the perfect crystal lattice, which is extremely difficult because it requires extremely high stress, shear stress, even approaching the theoretical shear strength, which is the shear modulus roughly divided by 2 pi or 10. And this would actually be around 10 to 20 gigapascal. And of course, the second thing would be we need to select the materials, especially for room temperature deformation, in a smart way. So that means we need to choose the material that already can show some good ductility, at room temperature, for example, the rock salt structure, sodium chloride, magnesium oxide, perovskite, strontium titanate, potassium niobate, and even zinc sulfide, etc. And once we have overcome these two components, and the third part for the dislocation multiplication, as later will be shown through cyclic loading, it actually becomes rather easy. Again, as I mentioned just now, we need to avoid dislocation pile up, which would actually also lead to crack. So I will give you some concrete examples to say the homogeneous dislocation nucleation criterion, and also the dislocation multiplication by focusing on strontium titanate, which already show very good room temperature dislocation mobility. So before I begin with the examples, I would also like to point out that the mechanical deformation, actually the boundary conditions matter a lot. By boundary conditions, I mean the temperature, texture, being either single crystal or polycrystal, the length scale, are we talking about nanoscale, microscale, or even bulk scale, pressure, external field with light or without light, with electric field or without electric field, etc. So I would like to narrow down my discussion and presentation to room temperature deformation, focusing on single crystals and also at ambient temperatures and conditions and pressure, etc. And to show you the capability of engineering dislocations across the length scale, meaning that from nanoscale even up to millimeter-sized samples. So we begin with the dislocation nucleation, as I mentioned, generating dislocations from 0 to 1. And here I would like to present you the so-called the nano-indentation pop-in technique, which is actually the knowledge and skill set already established from metals. That's where I used to work 4 years ago before I started working on dislocations in ceramics. So here is one representative curve from the nano-indentation test, where you can see in the y-axis, you have the load recorded. In the x-axis, you have the displacement recorded. So simply put, you are just pressing a very sharp indenter into your material where your machine is able to record the load and displacement simultaneously. So imagine that you have your indenter material. Very often it's diamond pressing into your material. And at the beginning, the material deforms elastically, and all of a sudden you see this so-called the pop-in event, or the strain burst we call in the nano-indentation community. And this is actually a signature of the elastic to elastoplastic deformation. And after that, the material started to deform also elastoplastically. And in metals, it has been well established that this pop-in event actually corresponds to the dislocation nucleation, meaning that originally underneath the samples, underneath the indenter, we have a dislocation-free region, and this popping event actually correlate to the dislocation generation or nucleation. And of course, there are quite a number of equations to compute the stress level corresponding to the specific point when this instability occurs. As you can see, the maximum shear stress required for this popping event to happen, or the so-called the nucleation dislocation, in this case, is around 14 to 18 gigapascal. So, and in our case, if we look at strontium titanate, and this is just to show you an example, the starting material here and all the yellow arrows pointing into the pre-existing dislocations reviewed by the old technique, chemical etching. So these are the dislocations interacting with your surface, and the local atoms are removed, so you can see the etch pits. So they correspond to location of dislocations. As you realize that most of the regions actually are dislocation free. That means if we are going to place a very sharp indenter, for example, with a tip radius of roughly 90 nanometer, and we have extremely high chance of putting the indenter into a dislocation free region, what happens is that we see the similar curve, load displacement, first deform elastically, as can be captured by the Hertzian fit, and then all of a sudden you have a jump here. So by computing the stress level corresponding to this event, we see actually also 14 to almost 18 gigapascal stress level, even for different strontium titanate samples with the different stoichiometry. So what does this mean? Can we also just directly transfer the conclusion from metals saying this is corresponding to dislocation nucleation? And we need to be sure about that. So we went ahead and even tested different tip radius here. For example, 100 nanometer, 2 micron, 5 micrometer, and 25 micrometer. The interesting thing is, for the very sharp indenter, as we call it, with the tip radius below 2 micron, we see all the dislocation edge pits here, showing no cracks. But if we started to look at the 5 micrometer indenter tip, 25 micrometer indenter tip, we see both dislocation edge pits and also the cracking. So obviously there is a so-called the new pop-in size effect. So depending on the size of the tip, we actually can either generate a completely plastic deformation, or there's the coexistence of plasticity mediated by dislocations, also cracking. So they are the corresponding load displacement curves, and I will not go to the details, but rather to show you in the ideal case, meaning that we have a very sharp indenter, what would be happening underneath the indenter with respect to the stress level. So simply put, if we have a very sharp indenter probing into a local region, we can assume that the local surface can be almost perfect, meaning that there is no crack and there is no pre-existing dislocations. And based on the contact mechanics, we can actually compute the maximum shear stress underneath the indenter. Very often it's happening in this region, as well as the maximum tensile stress happening here. We assume that the maximum shear stress is responsible for shearing the bonds, to break the bonds for the dislocation nucleation, while the maximum tensile stress is responsible for breaking the bonds for creating cracks. And when we compare them to the theoretical fracture strengths and theoretical shear strengths, we realize that actually the applied maximum shear stress can easily achieve the theoretical shear strength to break the bonds to induce dislocation activities even before the materials can actually induce the cracks. So this somehow explains the very sharp indenter that can generate the dislocations without creating cracks, but we are still working on what is happening with the larger tip indenter for the coexistence of cracking and plasticity. And of course, we're not satisfied just working on one material system. That's why we went ahead and also tested barium titanate and single crystal titanium dioxide. It shows consistently that if we are able to engineer to use a sharp indenter, we will always be able to generate dislocations purely without cracking. But if we go to certain tip radius that is larger than a critical value, we started seeing both dislocations and cracking. And there is also a very interesting application actually based on this technique, which I will show you later. So the next step would be we move on, and we were thinking about what happens if we use a much, much larger ball indenter, in this case, 2.5 millimeter. And the interesting thing happens, again, is it does not show cracking anymore, but rather, again, pure plastic deformation. And we also started doing the so-called the cyclic indentation, meaning that this is 1x means one time indent, 5x means 5 times indenting in the same location. So we basically loaded, unloaded, and loaded and unloaded to 5 times, even up to 50 times. So as you may see that the slip traces here, all these lines, vertical, horizontal lines, they actually are the indication of the plastic deformation. And when we take a closer look, again, using the chemical etching technique, we started to see that the dislocations, the densities are increasing. For example, here is the pristine sample where you barely see some of the dislocations, and after 1 cycle, we see a lot more. After 10 cycles and 50 cycles, we see many, many more. And also there seems to be a saturation of the dislocation edge pits. So we plotted the dislocation edge pit density as a function of the number of cycles, and we started seeing that there is almost 1,000 times increase in the density compared to the reference sample. And also there seems to be a saturation after roughly 10 cycles of indentation. And we would like to point out that in this case, dislocation multiplication is happening, because that means that we have a handful of dislocation in the beginning and they are multiplying and generate many, many more dislocations, which is actually very helpful for our dislocation-based mechanical and functional studies at a later stage. So again, we are not satisfied just working on strontium titanate, so we extended the method actually also at room temperature to another material, potassium niobate. As you can see, all the slip traces and dislocations, and magnesium oxide, zinc sulfide, zinc oxide, calcium fluoride. where you can see the slip traces here and here and here inside. So based on the size of the plastic zone and also the load, it's 1 kilogram or 1.5 kilogram and the size. So we can basically easily compute the mean average, let's say the shear stress underneath, which is usually hundreds of megapascal. That's a strong indication that for this specific materials we are presenting here, their dislocations actually can move rather easily, even at room temperature. So we are also constructing the material database and using this fast sampling method. Again, the point loading using the indentation technique is not sufficient to generate a much larger plastic zone. That is why we started extending the indentation to stretching. And here I show you the cyclic stretching method. And this is one cycle just for reproducibility, 5 cycle, meaning that we stretch once, back and forth 5 times, and back and forth 10 times. Again, you can see the slip traces, the signature of the plastic deformation. For 1 cycle, it's rather discrete, and for 10 cycles, the density gets higher and higher. So that's, again, an indication of the high dislocation density. So this time, we do not use the old chemical etching technique anymore, but rather directly show you the transmission electron microscope images, which we take the samples perpendicular to the surface within the wear track. And you can see that after 1 cycle, the dark lines are the dislocation lines. We have a couple of dislocation lines that, and after 5 cycles, many more, 20 cycles, way more than what we can imagine even before we see these images. And just to give you a brief idea, so here we roughly have almost 100,000 kilometer length of the dislocations within 1 cubic centimeter. And also we would like to point out that there is no crack formation in this case, and all we achieve this at room temperature. And this is the case study on strontium titanite. And of course, again, we extend it to another material system, for example, magnesium oxide, zinc sulfide, and calcium fluoride, etc. So we really can see the general applicability of this technique, the cyclic indentation, also stretching, for generating a much, much larger plastic zone and also a much higher dislocation density. So just to quickly summarize, this is the toolbox that I briefly mentioned at the beginning. Across the length scale that we are able to generate plastic zone size of hundreds of nanometer with the nano indentation technique at the very beginning, and now even up to centimeter, of course, in length plastic zone. And of course, we can tune the dislocation densities as well, even up to 10 to the power of almost 15 per square meters. So this actually gives us a very nice platform now to use the dislocations for what we mentioned at the very beginning for the functional and mechanical studies. For instance, here, the dislocation-tuned mechanical properties, I focus on the improved fracture toughness in strontium titanite. So we first induce the dislocations, and then we put the vigorous indents into the plastic zone and see that the crack lengths actually start to decrease compared to the dislocation-free region. And this is a strong indication that the fracture toughness, or let's say the resistance to the crack propagation, has been increased. And this is good news, of course, for ceramic materials. And also we see a similar trend for potassium niobate. After engineered dislocations, we also see the crack shortening, which is even much stronger than strontium titanite. And also we even see almost 2 or 3 times higher the fracture toughness in the dislocation rich regions compared to the dislocation poor regions. And what's more interesting is if we look at the magnesium oxides, once we engineer the dislocations within this region, as indicated by the dashed lines, where after 1 cycle, we have a rather low dislocation density, up to 25 cycles, very high dislocation densities. What's interesting is the cracks even completely disappeared. So that means we have a much, much higher damage tolerance if we can pre-engineer high dislocation densities. So this is a little bit intuitive, maybe. That's also why we call it the deform to perform. So first we plastic deform the material, and second, it performs much better with respect to the mechanical properties. And I would also like to take a few more minutes to show you the dislocation tuned functional properties. And this is the technique I briefly introduced at the beginning. that using the nano-indentation technique for the popping studies, where we can engineer a lot of dislocations, overlap the indents, and to have a larger plastic zone. And then we can also see that the dislocations we engineer at room temperature actually can improve the electrical conductivity by almost 50%. And another case is to use the pre-engineered dislocations to decrease the thermal conductivity, which is actually also very important for thermoelectric figure of merit. So in literature, it has been predicted that we need a dislocation density of almost 10 to the power 15 per square meter to see an impact of the dislocation reduce thermal conductivity. And all these dots here are the experimental data, which actually has a rather low dislocation density. So a decrease of the thermal conductivity was not really seen. And in our case, as I showed just now, we were able to actually engineer a density up to 10 to the power of 15 per square meters, which actually really now shows us a rather very appreciable decrease of the thermal conductivity, even by almost 50% compared to the pristine samples. So to quickly summarize, I would say ceramics can be ductile at room temperature, contrasting the conventional picture that ceramics are brittle, and even at bulk scale. So dislocations in ceramics may be underappreciated, and this topic is also gaining its momentum with respect to dislocation to mechanical and functional properties, as you can see here. So in this talk, I showed you some of the details and counterexamples that we focus on room temperature mechanical deformation to engineer dislocations, particularly by examining the deformation boundary conditions by looking at dislocation, nucleation, multiplication, and motion, as well as suppressing the crack formation. We can actually achieve plastic zone size up to centimeters in length, and also with a density even approaching 10 to the power of 15 per square meters, which really serves as the platform for a lot more dislocation-based studies. And of course, we are not just satisfied with what we have now, and we are really keen to identify more ceramics that can show even room temperature bulk plastic deformation, and to maybe help to change your view towards the so-called brittle or ductile ceramics, even at room temperature. So I hope that I have successfully triggered your interest in this topic, dislocations in ceramics. In case you are interested, I would really like to recommend you to some of the work that has been mainly done actually by my master students in the last several years. And also, in particular, this overview article, these two overview articles invited by the JACerS bulletin, and also this article I mentioned at the very beginning for the second century Trailblazer. And with this, I would like to thank you very much for your attention. And also, this is the last slide I have to really make the acknowledgement to all my collaborators, and especially the students around the world, without whom I would not be able to achieve this. Especially most of the work actually has been done since 2019, and most of the work has been done during the Corona pandemic, which has been rather a difficult time. And yeah, the credit also goes to my collaborators and my students. Thank you very much.